Okay, we'll start now. Even though the attendance is poor, okay, only 36, 35 members are joined, even less than 35 members. Anyway, so I don't bother about that. We'll start our class now today. I think again we are taking up this class after a long break, maybe more than 1 month. I think you might have recalled all those things what we had discussed in case of these welded joints. We'll continue that. Today we'll take up the analysis of welded joints subjected to eccentric loading. Again, in case of eccentric loading, there are different ways of applying eccentric loading to a welding joint. So in that, first we'll consider if the eccentric load is in the plane of the welds. If the applied eccentric load is in the plane of the welds, how we are going to analyze or how we are going to design the weld for this purpose. So for that, the design of welded joint subjected to an eccentric load in the plane of the welds consists of calculations of primary and secondary shear stresses. If you recall what we discussed in case of riveted joints, there the riveted joints are also when a riveted joint which is subjected to eccentric load, then there we have seen that the rivets are subjected to primary and secondary shear stresses, and we have seen the procedure how we can calculate the magnitude of the primary shear stress and the magnitude of the secondary shear stress. Here also the principle is same, because the weld is subjected to eccentric loading in its plane, so it will introduce a primary and secondary shear stresses. So how we can calculate the primary and secondary shear stress? Once we computed the primary and secondary shear stress, you need to find out what are the resultant shear stress due to this primary and secondary shear stresses. Then based on that you can design the joint. So for that, let us take an example how we can analyze a welded joint which is subjected to an eccentric load in its plane. So for that we'll consider a bracket. Okay, here this is a picture of that. I have a bracket which is subjected to an eccentric force P attached to the support by means of two fillet welds W1 and W2 as shown in figure. So now if you take this, so this is a bracket, this one is a bracket. So this bracket is welded to this wall through two welds. So here these two are parallel fillet welds. So okay, we won't call it as a parallel fillet, then simply we'll call it as a fillet weld. When we'll call it as a fillet weld is if the parallel fillet, if the line of action of the force is parallel to the length of the weld, we'll call it as a parallel fillet weld, or else if it is perpendicular, we'll call it as a transverse fillet weld. Of course, here they look like a transverse fillet welds, even though the load is eccentric. Okay, so now, so here you have a fillet weld, so denoted by W1 and W2. Now this bracket is subjected to a force P here, and which is making or which is having some eccentricity E from the centroid of this weld. So here we need to find out what is the CG or center of gravity of this weld based on its thickness, throat thickness, or maybe the thickness. So from that, let us take it is having an eccentricity of E. So in that case, how I can compute the primary shear stress and the secondary shear stress? So like I already told, the procedure here is in such problems, the first step is to determine the center of gravity of the welds. So that means first you need to identify what is the center of gravity of this weld. So while calculating the center of gravity, what you have to do is you need to assume the weld as a line. So that means if I take this one as a line, this weld as well as this weld, or for that matter, any weld, if it is present, will treat the weld as a straight line or line. So by treating it as a straight line, we will try to find out the center of gravity. But here, one more thing here is, we have an advantage here. No need to calculate the center of gravity for this weld. So using any formulas or anything, something like that. Only thing is, if you are able to use the data book, in the data book he has given all the weld types. Maybe here it is only 2 welds. Maybe sometime you may have one more weld here also. Like here also 4 welds are there. So like that, different combination, different shapes are there for the welds. So in the data book, he has provided for all types of welds, for maximum possible extent, for all types of welds, how can you calculate the center of gravity, provided if you know the length of the welds. So here length of the W1 and length of the W2, if you know that, you can, and also if you know this vertical height. So from this, in the data book, for the given weld configuration, you have a formulas for X bar as well as Y bar. So center of gravity is denoted by its X and Y coordinates. X coordinate is denoted by X bar and Y coordinate is denoted by Y bar. So only thing is, you need to compute Y bar and X bar. For that, what is required is, you need to know how to use the data book or how to identify the suitable formula for calculating the center of gravity. So for that, only thing what you need to do is, you need to identify what is the given weld, so corresponding weld in the data book. So from that, straight away you can pick the formula for that. Once you pick the formula, take the data from the given problem, substitute that data into that given formula, you will get your X bar as well as Y bar. So like that, first we'll find out the center of gravity of the weld system. Then once, suppose if G is the center of gravity of the 2 welds and E is the eccentricity between the center of gravity and the line of action of the force. Now, since this force is an eccentric force, then what we need to do is, we need to find out what is its effect on this weld. So for that, the same thing what we discussed in case of riveted joints, here also we'll do the same thing. You need to transfer this force from this location to its center of gravity. So we know when a force is transmitted from one plane to the another plane, the net effect is a force of magnitude, same magnitude. In addition to that, you have a couple also. So that means if I transfer this force P to this G, then what happens? Its effect is going to be, here I have a force whose magnitude is same as the original force, that means P. In addition to that, this P into E, that is nothing but a couple which will be applied to this center of gravity. So which is P into E. So that means if I transfer a force from one plane to another plane, the net effect is a force plus a moment. So force magnitude is same as the applied force, and the moment is the force multiplied by the eccentricity. So I can calculate now this P and E. So this P, direct force, this we call it as a direct force. So because of this direct force, it will create a direct shear stress in the weld, because this force is acting in the transverse direction to the weld. So it will create a shear stress. That shear stress we'll call it as a primary shear stress. So we know direct stress formula. Direct stress is nothing but load by area. If a load is here itself, P itself is the load, P by area of the weld. Again, here we need to compute the area of the weld. To compute this area of the weld, you should know what is the length of the weld and what is the thickness of the weld. If you know that, you can easily calculate area into thickness is nothing but your weld area. So once I know the area, so the load is given as P, so I'll get the primary shear stress. Then, because of this couple of magnitude P into E, what type of stress it is going to produce? That is the first question. Then, what is its magnitude? So that is the second question. So as you see here, this couple or moment will act in the direction of this jet. If I take the direction is perpendicular to the plane of this paper, so it will induce a torsion. It will induce, this is a torsion moment, and it will induce a torsional shear stress in the weld. So now, using your torsion equation, you can find out what is the magnitude of the torsional shear stress also. Anyway, we'll see that one by one now. So this is what I discussed so far. So this is the actual given application. So that means a bracket which is subjected to an eccentric load P here. So first we identify the center of gravity of this weld system, given weld system. Then we transfer this load from this location to the center of gravity of the weld system. By doing so, I got a force. In addition to the force, a couple or moment. So magnitude M. So again, if I split this one into two things, so that is because I have two loads here. One is a direct force, so another one is a couple here. So here we'll use the principle of superposition. That means what I can do is the effect of this combined loads is nothing but the effect of sum of the primary force or direct force plus the effect of the moment. So that is what we call it as a principle of superposition. That means instead of directly calculating the combined effect of this force and moment, what we'll do is we'll calculate individually what is the effect of this force P and what is the effect of this couple M. Then after calculating individual effects of this force and couple, then we'll add those two things so that we'll get the net effect or resultant effect of these two things. So that's what shown here in this picture. So, okay, according to the principle of our applied mechanics, the eccentric force can be replaced by an equal and similarly directed force P acting through the center of gravity along with a couple lying in the same plane. This is what I already discussed. So, the effect of the force P and couple M are treated separately as shown in figure. That's what I said here. So, we'll use principle of superposition. So, to find the effect of both. So that means just first we'll consider the effect of P separately and M separately, and then we'll club that so that we'll get the net effect or resultant effect of these two things. So first if you consider the first primary force. So here this is my weld 1 and this is my weld 2. So now this is the center of gravity what we calculated for the weld. So it is subjected to a direct force P here. So because of this, the resistance is going to be opposite direction. You are applying a force, then obviously the reaction to that force is going to be the opposite direction. So therefore, your primary shear stress will act in the vertically upward direction, provided your applied force is vertically downward. Vice versa, if it is upward, automatically the reaction should be downward. So here it is a distributed stress. That means throughout the length of the weld it is uniform. So it is not going to vary from point to point. It is uniform throughout. So you can see that the arrow, based on that, these are equal height of arrows. So that means its magnitude is constant throughout the length of the welds. So here as well as here. And how we can calculate that magnitude? Just like I already told, the area of the weld divided load P divided by the area of the weld. So that's what I shown written here. The stresses in the weld joints are shown in the figure. Okay, the force P acting through the center of gravity causes a direct shear stress in the welds. It is called the primary shear stress because it is a direct force. So it will create a direct shear stress. That shear stress, because here more than one shear stress is there, that's why we are naming this one as a primary shear stress. And it is assumed that the primary shear stress is uniformly distributed over the throat area of all the welds. So that's what I said here. So the primary shear stress is uniform. That means if you choose any point in the weld, its magnitude is same. It is not going to change from point to point. So for all the points, the magnitude of the primary shear stress is constant. So that is, and the magnitude of the primary shear stress is given by, we'll use tau1 is the notation for the primary shear stress. So this tau1 is given by P by A, where P is the applied load and A is the throat area of all the welds. So that means if you have two welds, you need to calculate the throat area of the two welds. 3 welds, you have to calculate 3 weld areas, like that. Depending upon the number of welds in our given problem, you have to identify, you need to calculate area of all those welds, then you need to sum up so that you get the total area of the welds. So once I got the total area, this P divided by the total area is nothing but your primary shear stress. So that means now we are in a position to calculate the magnitude of the primary shear stress. That means we already identified the effect of the direct force P. Then next comes, what is the effect of this couple or movement M? So here from this picture you can clearly see that this is going to be a twisting moment. So this twisting moment will create a torsional shear stress. We know from the torsional equation that shear stress is not uniform. So it is a function of radius. So if you take your torsion equation, what is your torsion equation? E by J is equal to tau S by R or tau by R. So if I take tau S, if I write expression for the torsional shear stress, that is tau S, which is nothing but E by J into R. So now if this R varies, T is constant, okay, of course. T is nothing but this movement M or T or M, whatever may be, twisting moment or movement. So this is constant. Even for a given weld configuration, this J is also constant. If R varies, that is R is nothing but distance of the point from the center of gravity. So this is our center of gravity. If I choose one point here, its distance is different. This is R. If I choose point A, this distance is different. So that means R is not constant for all the points. If R changes, obviously the shear stress will also going to change. So that means unlike your primary shear stress, your secondary shear stress is going to vary from point to point. Whereas your primary shear stress is uniform. That means it is constant for all the points, and the secondary shear stress is going to vary from point to point, and also it depends upon its distance from the centroid. So if it is close to the centroid, it is going to be smaller in value. If it is away from the centroid, means farthest from the centroid, its value is going to be more. So obviously while designing the system, always will get designed for the maximum stress conditions. So that means always we need to identify what are the farthest points in our weld so that you can get the maximum torsional shear stress value. So by doing so, I'll get the torsional shear stress. Once I got the torsional shear stress, then we'll go for the resultant shear stress. So those calculations I have shown in the next slide. See here, the couple M causes torsional shear stress in the throat area of the welds. They are called the secondary shear stresses. So because we already named the shear stress due to direct load, we'll call it as a primary shear stress. So that's why we are named it as a secondary shear stress. And this is given by, like already told, as per our torsion equation. So here I have used M for the torsion. So M by J into R, where R is the distance or radius of the point from the center of gravity. So R is the distance of a point in the weld from G. Hello? Class lo unna sir. Given by tau 2 is equal to M into R by J. R is the distance of point in the weld from G. So you can clearly see that if I take point A, so now I need to join point A to Z, then this distance I will treat it as R. Similarly, J is polar moment of inertia of the welds about the center of gravity of that weld system. So about this point Z, you need to calculate the polar moment of inertia. So far we know the formulas for polar moment of inertia for a regular section. That means, suppose if I have a solid circular section, for this I know polar moment of inertia J is nothing but 5 by 16 d cube. Sorry, 5 by 32. Polar moment of inertia is 5 by 32 into d power 4. If it is solid circular cross section. If it is hollow circular, also I know the formula 5 by 4 into d naught power 5 by 32 into d naught power 4 minus di power 4. Or else if it is a rectangular section, I know this. If the rectangular having dimensions b and h, so your polar moment of inertia also you can easily calculate for this also. Like this, not only rectangle, you can take any other shape, something like I section or T section or J section. For all those things, we know how to calculate the polar moment of inertia. But here the thing is, in case of these welded joints, you don't have those standard sections. So let us take for this simple, for this one, here you have one weld something like this, another weld is something like this. So here, this is not a I section, this is not a T section, this is not a circular cross section, or for that matter, any regular section for which we have already have a formula. So that means, so here again, the another thing here we need to remember is we need to compute the polar moment of inertia for a weld section, which is not a regular one. The weld section is not a regular one. Sometimes you get something like this. Sometimes if I take the weld, here this side also you may have a section something like this also. Some kind of C section or maybe some other section also. But the thing here is, so again to calculate the moment of inertia, polar moment of inertia for these three sections, what we'll do is, actually you need to use the principles of mechanics. So to compute that, so instead of going for that, what we'll do is, again here also we'll make use of the data book. Right. So if you have a data book, in the data book, for the like already told in the beginning, so identification of G, center of gravity using data book. So there itself he has given the formulas for this polar moment of inertia also, J also. So that means once you know how to use the data book, so if you refer to the appropriate formula or appropriate table in the data book corresponding to the given weld section, from that directly you will get the formula for centroid as well as formula for this polar moment of inertia J. So only thing is you need to pick the formula from the data book, and from the given problem you need to identify the data what we need to substitute into that formula. So once you know that, you can easily calculate J value. So M is known and J is known. Then next thing is you have to identify what is the R. So for that, what you have to do is you need to calculate at a different points. You need to choose in the your Venn diagram, like here A, B, C, D, something like this. In those things also, again what you have to do is you have to identify which point is going to be the farthest point. So that means by calculating the distance of that particular point from the center of gravity, easily you can know which is going to be the farthest point. So once you know all these things, you can easily calculate your secondary shear stress. So that's it. So the secondary shear stress at any point in the weld is proportional to its distance from the center of gravity. This is what I already told to you. Obviously, it is maximum at the farthest point such as A. So this is also already explained to you. The resultant shear stress at any point is obtained by vector addition of primary and So the resultant shear stress at any point is obtained by vector addition of primary and secondary shear stress. So what is this vector addition? So in case of riveted joints, we already discussed about this primary and secondary shear stress, how they are going to add. So one way of doing is, okay, vector addition is nothing but it's a vector mechanics. So that means if you know how to join the vectors, either you can go for analytical or you can go for graphical also. That means if you go for the graphical solution, first you need to draw the two vectors which corresponding to primary and secondary shear stresses. Then you apply your parallelogram law to add those two vectors. That is one way of doing it. Or else instead of going for the graphical method, you can use the analytical formula also. So what is the analytical formula here? In case of riveted joints, whatever formula we use, We'll use the same thing here also. That is tau R. That means the resultant shear stress. So this is the resultant shear stress due to tau primary and secondary shear stress, which is nothing but it is given by tau 1 square. Tau 1 is your primary shear stress plus tau 2 square. Tau 2 is your secondary shear stress plus 2 into tau 1, tau 2 cos theta. So this is the formula. Using this formula also you can calculate the resultant shear stress. This is nothing but the vector addition only. So if you apply that vector addition principle, the resulting formula is going to be only this. That's why I said it is the resultant shear stress at any point is obtained by vector addition of primary and secondary shear stress. This formula is derived from this vector addition only. So therefore, once I know, so that means I will calculate tau 1, that is the primary shear stress. I calculate the secondary shear stress, which is tau 2. And also I need to calculate what is the angle between tau 1 and tau 2 also. That is also important here. If I know that angle, then only I can use this formula. Otherwise, you need to go for the graphical method. So instead of going for the graphical method, what we'll do is, it is not that much difficult to calculate this theta value. So we use analytical relations, we can calculate this theta value also. Once you have done that, we'll get the resultant shear stress. So based on the resultant shear stress, if you ask to find whatever may be the throat thickness, generally in all these problems, this J is a function of your throat thickness. That means if you write the formula for the polar moment of inertia, it is a function of a throat thickness or maybe the thickness of the plate. So then here this is unknown. So if you ask you at the 3105. If you ask you design the weld joint means, you need to find out what is the throat thickness. So therefore in this formula for J, T is unknown. Again, if you calculate the area and the primary shear stress, the formula for the primary shear stress, it is going to be load by area. In that area also again that T is going to be unknown. So your area is nothing but, if you want to calculate this total area, that is nothing but the thickness into length of the weld. So here this T is here also unknown. So that means whatever expressions you got for tau 1 and tau 2, they are in terms of unknown T value. So now if I calculate that, so from this I will calculate the resultant shear stress. Once I calculate the resultant shear stress, this tau R, again this is also in terms of your unknown T value. So now to find this unknown T value, what we need to do is, they will give you some allowable shear stress in the weld. So you need to equate this resultant shear stress to the given allowable shear stress, tau allowable. So from this, we will calculate what is the thickness required or what is the throat thickness required for the weld in order to withstand the given load. So this is how you can proceed or you can solve or design a problem when a weld joint which is subjected to eccentric load in the plane of the welds. See here, this is important. Again, eccentric load may be applied in different ways. So this particular thing is, if the load is in the plane of the weld. So means what is the meaning of that here? If you see here, so this is the plane. This load in the weld plane only it is acting something like this. Suppose instead of applying this P here, something like this. Let us say if I take this is my x-axis and this is y-axis and this is z-axis. So then the weld plane is your xy plane. So here this is x-axis and this is y-axis. So the weld is in xy plane. So that means the load is also should be in xy plane. That means the load should be either px or py. It should have only x component or y component. It should not have a z component. That means if the load is applied something like this, if I apply load along the z direction, let us say this is the P. I cannot call this load is in the plane of the weld. So since your welds are lying in xy plane, this is my x-axis and this is y-axis. So your weld is, this dimension is in the x direction and this dimension is in y direction. Even for this weld also, this dimension is in x direction, this dimension is y direction. So that means my weld lies in xy plane. So therefore, your load should be in either in x direction or y direction. That means I can apply something like this. or something like this. So if I apply load something like this, I won't call this one as a eccentric load because it is passing through the centroid. Or else, maybe if it is not passing through centroid, I may have a option something. I may have a situation something like this. The load may act like this also. So this kind of thing we already see in case of unsymmetrical weld sections. We have already discussed this kind of thing. So therefore, here only thing is if the load is acting along the y direction. So something like this one, this line of action of this load should be away from the center of gravity of the load. Then only I can say that eccentric load in the plane of the welds. If that is, first you need to identify that whether the load is in the plane of the weld or not, and whether it is a eccentric load or not. If you identify that, if you are sure that the load is a eccentric load in the plane of the weld, then this is the procedure what you need to follow. So that's it. So this is how we are going to design the welds. So next what we'll do is we'll take up one numerical problem on this so that it will be much more clear to you. So okay, I'll go to that problem. Okay, so you note it down. This is our problem. You just note it down. So take a 2 minutes time. Then we'll discuss its solution also. So note down the problem along with the figure so that we'll discuss the solution. Now we start noting down it. ఇందులో కనిపించిందా అవి ఏది అదే ఇదే ఉండాలి లేటెస్ట్ ఇది కదా లేదా 10 నిమిషాలు అంటే క్లాస్ అయిపోతే చూద్దాం. Okay, is it over? Three zero nine.
Sir, completed, sir.
But nobody is responding.
Ivan, sir.
Sir, completed, sir. Not just one answer.
Okay, right. So okay, so the given problem is a welded connection as shown in figure is subjected to an eccentric force of 60 kilonewtons in the plane of the welds. Determine the size of the welds if the permissible shear stress for the weld is 100 Newton per mm square. Assume static conditions. That means you need to treat this load as a static load. It's not a fatigue load or cyclic load. It is a static load. That means its direction and magnitude always remain same. So now this is the problem. So what is the procedure? Whatever procedure we discussed so far, we need to apply that procedure for this. So that means first you need to compute what is the primary shear stress, what is the secondary shear stress. Then we need to find out what is the resultant shear stress. So then equate the resultant stress to given the allowable stress. So the allowable shear stress or the permissible shear stress he has given it as 100 Newton per mm square. So we need to substitute that. So for that, first we have to compute the primary shear stress. Primary shear stress is nothing but load divided by area of the weld. So here load is 60 kilonewtons is given. Area means, so he has given this length and this length as well as this length. So here this length he has given it as 50. So assume all dimensions are in mm. So even though he has not mentioned here, these dimensions are in mm. So 50, 100, 150. Even this is also going to be 50 only. So this 50 plus 100 plus 50 will get it as 200 into T is going to be the area of the weld. That's it. So load by area. I got the primary shear stress. Then we need to identify what is the center of gravity of this weld so that you can transfer this load from this location to this center of gravity. So to find that center of gravity, again you have to use your data book. So from the beginning onwards, beginning of the semester onwards, I am repeatedly telling you, you need to buy the data book. I don't know how many have your data book. So some people are following, what you can say, PDF documents. So those things are not as useful for you in the examination. If you buy the data book and if you follow, while I am teaching, if you open the data book and if you see, then only you will get something. Otherwise, if you do everything in the air, గాల్లో చేశారంటే ఏ గాల్లో చేశారంటే మీ నేర్చుకుని కూడా గాల్లో అక్కడి నుంచి అటే పోతా ఉంటుంది. So that is up to you whether you are using the data book or not, or whether you are going to buy our data book. I'm not going to repeat again and again. So that is what I can say is you should have that మీకు ఉండాలి కొనుక్కోవాలంటే డేటా బుక్. నేను ఎన్నిసార్లు చెప్పినా కొనుక్కోపోతే ఇంకేం చేయాలంటే నేను చేయగలిగింది లేదు అందులో. ఓకే, ఎనీవే, సో first we'll see how to compute this G for this for the given weld. So here the weld is something like a channel section, C section, it is something like this. So here you have to calculate what is the X bar and what is the Y bar for the G. So for that, okay, anyway, this is the given data. Primary shear stress, I already told you there are two horizontal welds, W1 and W2. So this is W1 and this is W2, and another vertical weld, that is W3. The center of gravity of the weld is given by, if you open your data book, in the data book this formula is given to you. So I have a data book with me. In my data book, so if you go for welded joints, of course whatever formula I written here, that is from the data book only. In the data book, okay, it is chapter number 10. In the chapter number 10, if you go for 10.1, that is symbols for SI units. Then next point, design particulars and equations, 10.2 is there. You go to that page. So in the 10.2 page, you can see all these things. Not only 10.2, okay, you can open 10.11. That is section modulus in bending and polar moment of inertia in torsion for typical welded connections, like that he has given. Maybe I'll show it to you through this. Then you can understand. Okay, maybe for that I need to come out of presentation mode also. Keeping myself. Now you can see that in the data book. So this is the thing what he has given. So if you refer this particular table here, he has given here different cross sections of the different sections of the weld. It's not cross section, only sections of the welds. Then section modulus is given. After that, polar moment of inertia is given. So we need to use these formulas. Section modulus will require later. So when the load is not in the plane of the welds, it will be subjected to bending moment. Because of bending moment, you have a bending stress. To compute that bending stress, you need to section modulus. But right now we require this column, that is polar moment of inertia formulas. So here you can see that here polar moment formula he has given J in mm power 4. These are the formulas for different welds. But coming to the weld, what he has given in our problem, you can see that here this is the one, serial number 6. You can see this is the weld what he has given in this particular problem. So for that, see from the diagram, after the diagram, he has given the formulas for x bar and y bar also. So x bar is L square by 2L plus B, y bar is B by 2. So that's what he has written. Then after that, you have a formula for section modulus. This one, section modulus formula, and this one, formula for moment of inertia. So I have to identify the given weld section. So for this problem, this is the section. Maybe from some other problem, this may be the section or this may be the section. Or for that matter, you have some more pages also there like this. So different sections are there. So from those sections, you need to identify what is your weld section, and you need to pick the formula from the data book for the given section in the problem. So here, like I told, x bar is given as L square by 2L plus B, and y bar is B by 2. So what is L, what is B also he has given. See in the diagram, if you see that, so this side he has taken it as B, and this side he has taken as L. So now, if you apply that formula, you will get the centroid as well as polar moment of inertia. So again, I'll go for presentation mode. So I'll take you to the presentation here. So this is what I written. So from the data book only, I written these formulas. L square by 2L plus B. L is nothing but the length, this horizontal length he has given this one as L, and from ear to ear this distance he has given it as B. So if I apply that, L is equal to 50, here B is equal to 100. So that's what I substituted in this. L is 50, B is 100. If I do that, I'll get x bar is 12.5 and y bar is B by 2. So B is given as 100. So B by 2 is going to be 50. So now I am able to identify the coordinates for this point Z. So that is from ear to ear it is 12.5 and from ear to ear it is 50 mm. So once I identify that, then the area of the welds, I need to compute what is the area of all these three welds. So for that, first weld. So if you want, you can give the numbering for all the welds. Let us say this is first one, and this is the second one, and this is the third one. Or else in the diagram itself, he has given the number. See here, W1. So this is the first weld. W2, this is the second weld, and W3, this is the third weld. So accordingly, the area of W1 will take it as A1. The area of W2 will take it as A2. The area of W3 will take it as A3. So W1 is nothing but 50 into T. W2 is nothing but again 50 into 3. W3 is 100 into T. So those are the areas. So that's what I calculated here also. So A1 is 50 into T. This is A1 50. This length is 50 into T. A2 is this one 50 into T. A3 is this one 100 into T. So now if I club or if I add all these three, I'll get the total area of the weld, which is nothing but A, which comes out as 200 into T mm square, because these dimensions are in mm. So once I got the A value, so load is given 60 kilonewtons. So then I can calculate the primary shear stress tau 1, which is nothing but P by A. So 60 kilonewtons, if I convert that one into newtons, it becomes 60,000 newtons. 60,000 divided by 200 T, which comes out as 300 by T, which is load is here, your load is in newtons and area is in mm square. See here the units, area is in mm square, load is in kilonewtons. We converted that one into newtons here. So therefore, the unit for your stress is Newton per mm square, which is comes out as 300 by T Newton per mm square. So that's about the primary shear stress. Then coming to the secondary shear stress, once you identify the G value, so first you need to compute what is the twisting moment M. So that is nothing but a load into perpendicular distance. So here he has given from this point to this point is 150, but you have a G here somewhere else. So always your eccentric distance is measured from the G value, not from the edge of the plate. So that means we already identified the G is located from this point to here. I have a G. Here G is there. Here this distance is 12.5. We got it as x bar is 12.5. So therefore, from G to this point, so this is going to be your eccentricity. This is your E value. So from this point to this point, it is 150 plus 50, 200. In the 200, if I subtract this 12.5, I'll get E value. So that means 200 minus 12.5 is going to be your eccentric value. So I got E value. Then load is given 60 kilonewtons. I'll convert this one into newtons, which becomes 60,000. 60,000 multiplied by this E, we get the moment. So that is twisting moment here. So that's what I done here. I found the same thing here. So first we need to calculate. Okay, so later. Okay, so okay, E is shown it as something like this. Either you can take 200 minus 12.5, or you can take it as 50 minus 12.5 plus 150. Either way, you are going to get the same thing. Your E is this value. So then your M is nothing but P into E, which comes out as 60,000 into 187.5, which comes out as 11,250 into 10 power 3 Newton mm. Why it is Newton mm? Because your load P is in newtons, E is in mm. Therefore, the resulting units are going to be Newton mm only. Okay. So then once I got this one, then to find out the secondary shear stress, I need to compute the R value, and also here this R value I need to consider is which should be farthest from your center of gravity. So now here if I choose this point or this point, so these 2 points, point A, or if I consider point here B, this point and this point is going to be the farthest point from the center of gravity. Other than this, if I choose any other point, it is going to be the having a less distance from point A. So therefore, I have to take the point A. So for this point A again, I need to calculate what is this R value, this distance. That is nothing but, if I treat this one as a right angle triangle, if I use Pythagoras theorem, Pythagoras formula, I can calculate this distance R. So that means, so here I'll treat this one as something like this. This is a right angle triangle. So this distance, this vertical distance is already given, that is 50, and this we already now calculated this distance. So this is 12.5. In 50 you need to subtract this 12.5, which is nothing but 37.5 only here. So now in order to get this R value, so that is nothing but square root of 37.5 square plus 50 square. So that's what I did here. 50 minus 12.5 square, that is nothing but 37.5 square, 50 square, which comes out of this R is 62.5. So now I know M, I know R. Next I need to compute this J value. So like I already to show it to you, from the data book I have to take this figure. I have to take this formula. So it is given in the data book, just now I already shown to you. So I picked that formula here. in this formula we know L and we know B. So L is 50, B is 100. If and you have a T is there, T is unknown. So I get the value of J in terms of T. If I substitute the data and if I compute it, I got J is 385,416.67 into T mm power 4. So now I know everything. I know M value, I know J value, I know R value. So now I can compute the secondary shear stress using the formula for the secondary shear stress, which is nothing but M into R by J. M is, we already calculated this, 11,250 into 10 power 3. And R we computed it as 62.5. So we substitute that. And J also we computed and the value for J is 385,416.67 into T. If I substitute all these values and if I simplify that, I get tau 2 as also in terms of T only. So and it comes out as 1824.332 divided by T Newton per mm square. Now we calculated tau 1 and tau 2. So then we need to find out what is the resultant shear stress because of this tau 1 and tau 2. So for that, the resultant shear stress formula is like already told. This is tau 1 square plus tau 2 square plus 2 tau 1 tau 2 cos theta. So that means you should know what is the theta value also. Now if you come to this diagram here, so here our tau 1 direction is something like this and tau 2 direction is something like this. So now this angle, so not this one here, this is shown, so also here also shown, this is the theta value. This value is same as this theta value. So we can easily calculate this theta value provided if I take this one as your right angle triangle here, something like this, tan theta formula, opposite side by hypotenuse. Sorry, opposite side by adjacent side, tan theta is the formula. Tan theta is nothing but opposite side. This side is 50 and this adjacent side, this is 25. Okay, not 25 here. So 50 minus 12.5. So that's what I shown here in this formula. Tan theta is equal to 50. This particular it is 50 and this horizontal distance from here to here it is 50. But in that you need to subtract this x bar. X bar, if you subtract, x bar is 12.5, you get your tan theta is R. Tan theta is 50 by 50 minus 12.5. From that you will get theta is equal to 53.13 degrees. So once I got all these things, then I'll take those data and substitute into this expression for tau R and I can simplify this. If I substitute tau 1, tau 2 and theta value, then if I simplify that, I got tau R as 20.2555 divided by T Newton per mm square. Now this resultant shear stress should be equated to the your allowable shear stress. Allowable shear stress he has given it as 100. So if you equate that one to that, you will get from that you will get the thickness of the weld. T is equal to 20.25 mm. But this is only the throat thickness. But what we need to ask in the problem is we need to calculate what is the size of the weld. Size is nothing but the throat of the weld or leg of the weld. We call it as size or leg of the weld. The relation between T and H is given by like this. H is equal to root 2 into T. So we already computed T value. Just you need to multiply this T by root 2. You will get the size of the weld, which comes out as 28.65 mm. So like this, you can solve the problem. So here I have taken only one section, C section or some kind of channel section. You may have a different kind of sections in the examination. You may get any other section also. But the only thing is the procedure is like this. If you follow this procedure like this, you can solve for anything. You can solve any problem also. So maybe what I'll do is I'll give you some exercise. I'll assign 1 or 2 problems on this. And I'll ask you to solve those problems and you need to upload through as an assignment for that one. So that you may get some advantage while evaluating your assignment papers. So I think I'll stop now today. It is already in the 10:15. So maybe we'll continue in the next class. In the next class, we'll consider another type of load. That is when the weld joints are subjected to, here it is subjected to twisting moment. If it is subjected to bending moment, how we can design the weld joints. So that we'll see in the next class. Okay, so I'll stop now. Then what you do is you need to upload whatever notes you have taken for the today's class to get that attendance. I think I already posted that attendance sheet. So just respond to that and then you leave the class. If you have any doubt, maybe we'll discuss in the next class because already it is 10:15. So we'll discuss, if you have any doubt, we'll discuss that in the next class.